All right, can you hear me now on the stream?
Sorry.
Sorry, those in the stream, they said they cannot hear me. I think I'm okay now. All right. Let me just finish one set.
Mhm.
Okay, that should be okay. All right. So energy. So do you still want to go?
Your
Right.
Wi-Fi. I think it's your Wi-Fi.
Okay, got that. Let me change hotspots.
Your camera freezes. Oh, it's moving now.
Okay. Hold on. I'm actually
Yes.
changing to my phone to my hotspots. Uh, yeah, yeah, it is. Okay. So anyway, let's go back. So today we're gonna do energy production first. Okay. Okay. Now, we're gonna go to the basics first, and then we're gonna go to the IB physics part afterwards. Okay. So for energy production, there are three. There are just the energy production section. There are three things we need to learn. Okay. The first one is types of energy sources. Okay. Now, when we say energy sources, it's gonna be about electric. How we use electricity. So types of energy sources. Okay. The second one that we're gonna go through is the different types of energy production. Now, this one is you should be familiar with the basics of this now. So this would include fossil fuels, geothermal, hydroelectric, those things. Okay, different types of electricity production or energy production. And then the third one, production. And the third one is energy density and specific energy. Energy density and specific energy. Okay.
Mm-hmm.
Let's start with the short ones. This is short, and this is short. This is kind of long. What I normally do with my students is I ask them to make reports on this because uh, if I do it all, it kind of gets monotonous. So I usually ask my students to do this. But anyway, let's go back to the. I think let's go back to this, the types of energy sources, right? So we know this already, but we can actually, what the thing that you have probably learned before, we can arrange them into two types, right? The first one that we already know is the non-renewable sources. Okay, so um, what would we consider non-renewable?
Mm. Oh, like uranium, like
Your mm-hmm.
fission. What's it
Uranium
called?
is non
Fission.
yeah, uranium is non-renewable,
I don't know
or
what's called.
and yeah, fission fuels, right?
Fission fuels. Yeah.
Or nuclear fuels. Actually, fission would be the better term. Okay, there's another main type that we could consider under
Fossil
non-renewable.
fuels.
Fossil fuels would be non-renewable. Okay. Um, so again, this is basic, so you should know this already. So under fossil fuels, we have coal, gas, and oil, right?
Yes.
That also means if we have the non-renewables, then we should have the renewables, right?
Mm-hmm.
Now, what will be
Renewable.
okay? What can we consider renewable?
Mm.
There's so many types, right?
Oh, solar.
Solar,
I mean, can't uranium be renewable just at a very slow rate?
Actually, if you really have to think about it, uranium is even less renewable than fossil fuels.
Oh,
Okay.
because you can make coal. It just takes like 500 years to make
Yeah.
charcoal.
Yeah, and even nature can make coal in like let's just say over like several thousand years, right? But uranium, you really have to mine it, and once you've used up uranium, it's gone forever, right? You have to wait for the
Mhm.
universe to produce more uranium. Okay, so solar is one, wind would be another one, right? For renewable. What else? Geothermal. What are the big ones? These are the big ones:
I don't,
geothermal and what was the one you
I don't
said?
know. I said
Hydro.
solar. Oh,
Yeah. Okay.
oh, okay.
These are the four big ones, but we still have a few smaller ones. We have biofuels. Then we also have solar, wind, what's this? Tidal. Okay. And what's the other small one? I think this is it basically. All right. Everything else are at the moment small scale. So this is one way for us to go through the types of fuels or the types of energy sources that we know. But there is another way to classify your energy sources. Okay, and this is the one that's more relevant for DP. Okay, so for IB physics, the more relevant one would be we can consider them into either primary or secondary sources. Okay, now it's a little bit tricky to know what this is if you just don't know what's happening. But the easiest way to think about this is for primary sources of energy. You extract it straight, and that's the energy you get. Okay, so you in other words, let's use green. The energy from the source is used straight away. The energy from the source is used straight away.
Is it biomass?
Okay. Um, Biomass would not. All of these could be primary sources. Okay. But I'll give you an
Mm.
example later of what we mean by that. The second one is for secondary sources. Secondary sources is you use the energy. The energy is used. Energy is used to produce. Sorry, it's not used.
Wait, yes, it
Energy
does.
is. Go ahead.
Also, don't have access to the channel.
Hold on. Let me save that for
I
now then.
also don't have access to.
All right. I'll
Okay,
just.
thank you.
Yeah, I'll save that. I'll share that right now. Hold on. Okay, so while I'm sharing, let me just say what I wanted to right there. So a secondary source of energy or a secondary type of energy would be like it's like a second step. So it's taking a while. All right. An idea here is that all of these things, the fuel, solar, wind, these are all primary sources. Okay, these are all primary sources. The secondary type of energy that we would be using here is electricity. So again, let me do that. All of these will be under primary, would be electricity. Okay, so there. That's again. So these are the two ways that we can separate or classify energy into either secondary or primary types. Okay, is this clear? I think this is pretty straightforward. Okay, Do you understand why
Yeah.
electricity is secondary? Uh, so let's just put that here. So electric energy is used to produce.
Because it has to something needs to be made in order to make electricity.
Okay, exactly. It's like the energy has to be converted to something else and then to electricity, right?
Yeah, chemical to electrical, right?
Mm-hmm. All right. So
But for,
this,
for primary, like fossil fuels, you could just start taking energy out of it.
you can take it straight from the source, basically.
Hmm.
All right. So, uh, I hope that's clear. Hold on. Let me change. Let me adjust that. Okay, that looks a bit better. All right. So that takes care of the first bit. So this is done. Okay. So we're gonna go through here. This is again the easier one between the ones that are left. Let's go through this briefly. Okay. Energy density is, well, what's density? When you just say the word density, what's the first thing that comes to mind?
Um, Electricity. Oh, energy
Density.
density.
Yeah, just the word density without the word energy.
Density.
Mm-hmm.
The water. I
Okay.
don't
And
know.
okay.
Solids.
Okay. What's the density of water? Let's start with that.
I. That's a good question.
It's actually a very easy number to memorize. It's 1.
10.
Okay. So I'm just gonna start with that. So
Just
water's
one.
density is equal to 1 gram per cubic centimeter. I'm gonna write it like that. Not the, or better yet, I think I'll just write it the more standard way. Grams per cubic centimeter, like this, right? The thing here is, when we say
Mm-hmm.
density, we are gonna divide something. This is basically mass divided by volume, right? So mass over volume. Okay. The idea of energy
Mm-hmm.
density is the same, but instead of dividing mass, what are we do? We're still gonna divide that by volume.
Mm-hmm.
Okay. So this is energy density. So what are we dividing with volume? Okay. Here we're gonna divide this by the energy output or energy extracted. Okay. So energy extracted per unit volume is energy density. I know it sounds a bit weird, but it's gonna become more clear when we discuss something very prevalent right now. Okay. We're gonna connect this to a modern topic or a modern problem. Now, before we go there, specific energy, this is defined as the energy. Same thing. This is gonna be energy extracted divided by mass. Okay. So these are the two definitions we need to go to. And normally in the textbook, you would see you would see like examples of different fuels being used and how much the specific energy is. I'm gonna put this into a real world context for now. Okay. All right. CJ, quick question.
Mm-hmm.
How many cars do you have? Well, your family. Do you have any cars?
Mm, we have three.
You have 3. All right. All of them, I believe, would be um, gasoline powered. All right.
No.
Oh, really? Interesting. What kind of cars do you have?
Well, we have okay. We have one not hybrid BM, which is
Okay.
like fully combustion.
Oh,
The other
nice.
is like hybrid, which can either be hybrid or specifically electric
Mm-hmm.
or specifically combustion. So there's
Okay.
three modes.
So 3 modes.
And then
Oh,
there's one that's just a EV.
okay. All right.
Yeah.
So, okay. So you have an EV, and then you have 2 hybrids, but they run on different modes, right?
No, one's a hybrid, the other's just a combustion
Oh,
one.
one's combustion, one hybrid, one EV.
Yeah.
Okay. Quick question. Which one do you take for short rides? Which one would you rather take for short rides? Like maybe within the city
Oh,
or
ooh. I would like to take. Actually, I just take the hybrid one everywhere.
you take the hybrid one everywhere, right? Actually, the hybrid one
Yeah.
would be the best option for, just being everywhere, right?
Yeah.
Why am here? Let me adjust my lights. There we go.
Mm.
All right, so hybrid. Well, just so you know, we I don't really believe in owning a car unless you use it every day, right? And I don't
Yeah.
get to use a car. I don't have to use a car every day because
Mm.
where
You're
we
close to school.
yeah, quite close. Maybe if we take a car ride, maybe it's about 20 minutes away.
That's pretty far.
Yeah, still pretty far, but the way that we work is that we just carpool with somebody. It's still cheaper than actually having your own car, right?
Yeah.
All right.
Mm.
So, if we were not carpooling with anyone, I would have bought our own car, and we would be using that car to go to and from school and everything, right? But
Mm.
okay, I'm the point here. Let's go. Let's get back to the point. Uh, I do have a motorcycle because
Oh,
errands and stuff. Errands are better run
yeah.
with a motorcycle. It's faster, more convenient, and everything, right? And
Yeah.
the motorcycle I bought. Do you have one, by the way?
No.
No. All
Oh,
right.
well, my dad has one,
Your
but I don't
dad
like
has
it.
one. Okay. Uh, is it like a scooter or like a proper motorcycle?
Like a really old, like Suzuki motorcycle.
Oh, okay, Suzuki one.
It's
Well,
like one of those sporty looking ones.
all right, great. Suzuki. Well, here's the thing. There was a time wherein I owned a combustion motorcycle as well. This was before I came here to Jakarta. And then now I just bought one. It's been with me for less than a month. I bought an electric.
Hmm. It's
Okay.
so cool, right?
Yeah,
You
it's
don't even have an exhaust pipe,
you know what I find so cool
so you
about
can't.
electrics? They're so quiet.
Yeah, it's
It's
kind of dangerous though if you're like swerving between traffic.
yeah, I don't do that because of that danger, especially with the electric being so quiet. It's really difficult to, just not swerve, but I try not to.
Yeah.
All right. Anyway, here's the point. Um, let's go to let's go to the thing now. There's a debate of there's still I don't know why the debate is still around. Yeah, there's a debate why to which one is actually better for the environment, electric or combustion. Have you heard that debate before?
Uh, like the cars, the vehicles themselves,
Mm-hmm.
like well, people like combustion engines because it sounds cool,
That's definitely
and
one of the best reasons to have a combustion engine. It sounds cool.
honestly, um, EVs have like a issue where like if you hit the brakes, the brake light takes a while. No, if so EVs have this thing where like if you're lifting off the gas,
Mm-hmm.
the car will like slow down,
Right.
but not it's not like decelerate. It's not coasting. It'll slow down.
It won't coast. Exactly.
And then the
Yes.
brake lights won't turn on. So
Mm-hmm.
it's not safe.
Right. So but that's more on safety issues which can be fixed with proper engineering, right?
Yeah, but it's still like that.
Mm-hmm. Okay. The main issue I have with EVs versus combustion vehicles is EVs are supposed to be more environmentally friendly than combustion. That's one of
Uh-huh.
the things, right? We're not gonna get into that debate because that's not our topic, okay? But another thing that a lot of people kind of go through is so we have environmental, we have safety. The one that I want to go through now is which one is actually better in terms of efficiency. Which one's more efficient? EVs.
Let's see. Yeah, EVs.
Okay, what's more efficient?
Because you don't have to go to gas stations and pay people. You could just charge, and you don't have to interact with anyone.
Mm-hmm. Or I'm
The
just
car.
gonna say I'm just say combustion engines. Cars. Okay. Now, what I'm gonna do here, there's a lot of factors that can go into this. You have what thing you just mentioned, and then you have the fact that you have to charge EVs versus you have to top up the cars, right? What I'm gonna go through
Hmm.
here is how much energy can I'm gonna focus on range. Okay, I'm gonna focus on range. Now, range basically is a function of how much energy your car can store, right? So it depends on energy storage, right? On energy storage.
Yes.
Now, when energy is stored in EVs, this would be in the battery, right? And in combustion engines, this would
Hmm.
be in the fuel, in the combustion engine, right? So the now,
Yeah.
okay, this is where I say that combustion engines win. Okay, combustion engines win in terms of range. I think we're all aware of this. Combustion engines are now the reason for
Yeah.
that is this: for the same mass, okay, the energy density, okay, for okay, let me look for particular values here to be sure that I'm getting it right. So now, anyway, while I'm pulling this up, the batteries used in most EVs now are lithium-ion batteries, right? Okay, and then most EVs,
Isn't that like very like flammable?
yes, they are. Okay, the energy density for a lithium-ion battery, okay, lithium-ion batteries would be around 300 kilojoules per kilogram. This is now quickly approaching. This is still getting better, but let's just say that this is the average energy density. No, sorry, this is specific energy. Specific energy. Yeah. So this is the specific energy of lithium ion.
Hmm.
Okay. But the specific energy of gasoline. Okay. Uh, okay, hold on. The specific energy of gasoline is 46 megajoules per kilogram. Okay. So for
Hmm.
so what does this mean? For each kilogram of fuel that you have, compare that to each kilogram of battery that you have, you're gonna get more bang for your buck for gasoline. Okay,
Yeah.
right? So this explains why gasoline is still preferred even though EVs have been around for hundreds of years. Actually, have been around far longer than combustion engines. EVs were the were more were invented first. Okay. It's just that
Hmm.
gasoline engines or any type of combustion engine for that matter are just a lot more powerful. So this is why a lot of people still prefer combustion engines. All right. So this means let's just put it here. More than 10 times more energy per kilogram, right? So on a long trip, which one would you rather get? Like 10 kilograms of this stuff, of 10 kilograms of battery, or 10 kilograms of gasoline? especially if you know you're gonna go a long distance. You might as well go for 10 kilograms of gasoline, and that's
Yeah,
why
it'll be a
the
lot more expensive.
Mhm. Yeah, it's gonna. That's the thing, though. It's gonna become a lot more expensive. There are other debates to that thing about EVs versus combustion engines when it comes to cost. But basically, you really have to take everything into account. But this is one of the things that people think of. "Ah, okay, I think I'll be okay. I'll just burn gasoline, especially for long hauls. All right. Okay.
Mhm.
So this is the idea. Okay, of specific energy. Similarly, energy density would have a similar idea, but instead of doing it per kilogram, um, spe- um, energy
Wait,
density
Mr.
would
Dennis, are you writing something?
yes. Yeah. Oh, hold
Oh,
on.
you're
Let
not
me.
screen sharing.
I'm not sharing the screen. All right, hold on.
Oh, I thought you were explaining it to
There we
me.
go. Oh, okay. I have two people on the stream.
Yes.
Well, one is I know one of the people. It's my sister. Hello. I don't know who the other one is.
Oh,
I don't know who the other one is. But anyway, energy density. Okay. So gasoline has about approximately, so for gasoline, the density of gasoline is approximately 90% that of water. So let's just say 900 kilograms per cubic meter, approximately. Okay. So that means 1 cubic meter is 900 kilograms, right? The density of lithium ion. I'm curious over that. Let me just get that here. Density of lithium ion battery. Kilograms per cubic meter. A lithium ion battery is that's energy density. No, no one's giving me a value for the actual thing. Here. Approximately for batteries, lithium ion, the density is approximately 1,600 kilograms per cubic meter. Okay, so you can see that it's also heavier per cubic meter. So which one would be better in terms of
for
energy
batteries.
density, right? So I'm not gonna go through this because again, this is just basically conceptual for now. But from here, you can see that for the same kilogram, right? So this would occupy more
Yeah,
volume per kilogram, right? Okay.
yeah.
So which one would be a higher energy density? Well, we can actually
Uh,
calculate that, but if we assume that they have the same amount of energy, right?
yeah.
Gasoline would still win in energy density because of the 10 times more energy
Oh,
per kilogram.
okay.
Okay, so gasoline, this will still give you approximately that gasoline has 10 times energy, right? Of energy, specific energy of batteries, right?
Hmm.
So this combined with the density of the gasoline and the batteries would still mean that gasoline still has a bigger energy density, more oomph for the same volume. Okay. All right. So that's the basic
Hmm.
concepts there. Now the last thing that I want to go through are the types of energy production. We know what these are. We've basically also covered it here in energy sources here, right? But basically what we need to cover for DP. So I'll skip the basics for that. Okay. So the idea here is an energy production. I'll go straight to the main points that are DP specific. So IB specific. Yeah.
Mm-hmm.
Okay. So for solar, what are the main concepts that you need for solar? The sun has an intensity, has a maximum intensity. That's found in the data booklet. Okay. So where is it exactly on the data booklet? Oh, Akira. Hi, Akira. You're here as well. Akira's one of my students. Okay, let me open the data booklet to see what exactly is in there. Okay. And then from here, solar. I'll just get the value later. Uh, the idea here is larger area, more energy extracted. Okay, because the idea is intensity is power per unit area. Okay, let me see if I can find that particular formula here. Okay. Okay, nope, it's not here. So okay, so that's the first one. The second one is wind. Okay, the one that's specific for wind energy in IB and for higher level physics or engineering is this formula. Okay, it's still loading. So while that's loading, there we go. The power is 1/2 times the area. Basically, the idea here is if this is your windmill, and your windmill has blades, so it has blades like that. No, it doesn't matter how many blades there are, but I'm just gonna go for 4 right now, make it easier for drawing. Okay. Now this has a radius r, right? So from here to here is
Mm-hmm.
the radius r. The area here is equal to pi r squared, and that's that area swept by the blades. Okay, so area swept by blades. Okay, now this is the density of air, and this is the speed of air, speed of the wind. Okay, now basically this is telling you that this is the maximum power extracted by a windmill. So again, the maximum power extracted by a windmill would be equal to this formula. We can derive this quickly, but this is based from the idea of kinetic energy. Okay. Uh, how is this kinetic energy? Let's just go straight to this. Okay. So remember that kinetic energy, this would be of the wind. I'm gonna write that would be equal to 1/2 m of the wind times v squared of the wind. I'll just keep that wind like that, right? So from
Mm-hmm.
here, if we divide this by time, so over t, this becomes power extracted, right? And that's exactly what we got here. So that's power extracted. This is gonna be the 1/2 is still there. Um, the mass can be described. So mass is equal to density times volume, right? So this is gonna be mass is m. Sorry, that's mass. Density is this, the Greek letter rho. Volume would be v. I'll make that big V for now, and then V squared over T, right? But here's the thing. If
Mm-hmm.
we look at the windmill from the side, basically, what's the volume? The wind is blowing this way, right? So the volume of the wind would be a per unit time would still be equal to the velocity. So I'll make this bigger. So volume of air per unit time, that will be equal to the velocity times the area. So small v. This is area. The volume is VA, right? So we can just substitute this V over T with V times A. 1 half rho um, A V times V squared, and there we get 1 half rho A V cubed. Okay. Now remember, this is maximum. Okay. Now in theory it can be maximum, but in practice we cannot extract that much. Okay. In Why? Because here to get this maximum, you need the wind to stop, right? Wind must be stopped. And can you actually do that when in a windmill?
Mm, no.
No. So in reality, we get much less than that. Okay. So,
Mm,
all right. So we have our two things, solar and wind. The rest is just gravy, basically. You just learn about it and done. But these would be the most um, IB specific things here. All right. The rest of it, I think it's better learned when it comes to actually looking at the different situations. Okay. So let's recap that here on the last bit before I give you some exercises. Just some simple questions. Okay. The last one would be fossil fuels. We have geothermal, right? Oh, we have one more. I forgot. We have the hydroelectric. It's not in the data booklet, but you can actually learn about this later. Okay. Hydroelectric, fossil fuels, geothermal. What was the other one I missed? Solar, wind. Let's just go back to this. We did solar, wind, geothermal, hydroelectric, biofuels, and tidal. Tidal basically would be similar to tidal would be considered here. Yeah. Of course, fossil fuels. This also would normally include nuclear and biofuels. Okay. Basically, you just for this, what you need to learn, what you need to know, it's just the flow of energy. It's from the fuel. The fuel is either burned or in nuclear. In the case of nuclear, it undergoes fission, releases energy. That energy, that heat, is used to heat water. So boil water. Okay. There are two ways to boil the water, but we won't go through that yet. Okay. So fuel and then boil water, and then that water turns to steam, and then the steam is run through a turbine, and that turbine spins, right? That turbine spinning spins a generator, and then that generator generates electricity. Okay, that is a horrible lightning bolt.
mm,
All right, so yeah, so this is always the case for all biofuels, all fossil fuels, and nuclear energy. Generator electricity. So just follow this sequence. You're okay. The only thing here is the fuel produces heat differently depending on the type. Okay. Now for geothermal, nothing new. Okay. For geothermal, it's very similar to this actually, but instead of using fossil fuels, you use heat from Earth. From Earth, then into boil water. Then it follows fossil fuels afterwards. Okay. Okay. Then the last one for hydroelectric, there's one particular case. Um, it's not in the data booklet, but I think it's in the textbook. Let me just get that here. Um, okay. In fact, one of my students did an IA on this. Okay, it's all database though. Okay. The power
oh, they're
output.
talking about magnetic.
Yeah, the power output
Wait,
of
Mr. Dennis, yeah,
sorry,
comments in the chat.
sorry, say that again.
There's people or someone asking in the chat.
Oh, okay, hold on, let me see that. What?
Magnetic coils, are those solenoids?
Um, yes, yes. So Akira, yes, I see that. Okay. Um, anyway, the idea here is no, they're not solenoids. They're literally just things that spin around, and when they spin something like this. So, oh, okay, let me just show you that. I have a good visual aid here. So basically, this could be considered your turbine. So whatever that thing is boiling the water, right? The water gets boiled, turns to steam, and then the blows onto this thing. And when it blows, this thing spins. Okay, and when this thing spins, this is the turbine. This turns the generator, and then the generator on the inside, it's got those coils and everything. It produces electricity. The generator bit is gonna be tackled in topic 5. Yeah, topic 5 for DP, which is about electricity. No, not even topic 5. It's topic 10 in HL. Okay.
Hmm.
All right. So yeah. So basically, turbine. So steam turns a turbine. Turbine turns this thing in the generator, and the generator produces electricity. Okay. All right. So going back, hydroelectric. The equation is a bit long. That's why this is not in the data booklet. Okay. But basically, this equation is based on earlier for what's this for wind energy for wind turbines. The power equation is based on kinetic energy. This is based on gravitational potential energy. Based on gravitational potential energy. Okay. Specifically, I'm not gonna derive this like I did before because this is such a long derivation, even though it's rather simple. Okay, but basically,
Hmm.
this is gonna be it. Okay, so we can actually ignore this bit if the efficiency is 100%, right? So density of water is given. The water flow. This is the volume of water per unit time. We have acceleration due to gravity, and then you have height. Okay, so so basically, what do you get? I'll just do it quickly. Where do we get the mass? The GH is obvious from MGH, right? This thing gives you the mass. Okay, so
Oh,
again, this is the. I'll just write this down. This gives you mass per unit time. Okay.
oh, Mr. Dennis, you're not sharing your screen.
Oh, sorry. Let me show that again. Okay. So
Mr.
there.
Dennis,
All right. Can you see it now?
thank you.
All right. So again,
Yes.
this density rho times q is equivalent to saying mass per unit time. And mass times g times h is mge divided by mass by time gives you power. Okay. All right. Everything else is again just
Hmm.
additional details, but these are the most important ones.
So it's like a combination of like
Sorry, say the last bit, please.
like this unit has like a lot of connections to other units.
Yes. In
So
all
like
honesty, I usually
this
start
unit
with the.
connects to like a lot of other.
Yeah, they do. They do. This connects to topic
You
5,
start with
and this connects as well to topic 2, which
and
is right.
yeah,
Yes. What else does it connect to? It actually
yeah.
also kind of connects to topic
7
4. Okay,
waves. Oh,
waves a little bit, not too much. This really connects to topic 8 is topic 7 as well when it comes to the nuclear energy bit.
hmm.
Okay, so all right, so these are the two easy parts for energy production. We'll end it here. I don't think we have time to do the exercises. We'll do the exercises on the next meeting. Okay. Efficiency is just how much energy you can get out of it, Akira, compared to how much you put in it. So if you put in 100 joules of energy, let's say 100 joules of energy in the steam, and then out comes 80 joules of energy in the generator, the efficiency is 80%. All right. So again, let's say this is the whole process. In comes 100 joules, and then the process connects it to the generator, right? And then the generator gives you 80 joules. Then efficiency is equal to 80 out of 100, and that's 80%. Okay. Um, the thing about efficiency is the more steps you put into a process, the less efficient the whole process becomes. So, so
Hmm.
we want to minimize the number of steps in the process. Okay. Uh, okay. What else? CJ, how about you? Do you have any other questions before we end?
No, that's
No.
good.
All right. So, okay. So exercises on the next meeting before we go to exercises, and then we go.
Sorry, your Wi-Fi just like cut out just now.
Okay. I have just reconnected again. Am I okay? Am I okay now?
Yeah. Yeah.
All right. So again, so we'll just end. We'll just go back there. So again, next time we have exercises, and then we'll go through global warming. It's called something else in the book. It's called something else in IB, but it's basically
Mhm.
global warming. Okay.
Okay. Do you know? Oh, is it like the albedo and stuff?
Yeah, yeah.
No.
That's all connected to that.
Okay. Do you know like how much of the exam, like how much of this topic is in the exam, like percentage?
Um. Okay. I'm gonna say that if this were the final exam in SL, you'd probably get 3 or 4 questions on this unit. Two for
Mm.
energy production and two for global warming.
Okay.
That's for multiple choice. So should be about the same percentage in the structured question.
Hmm.
Right. Okay, so okay, I think we can end it here, CJ. For
Okay.
now, we'll just continue next week. Not next week, on Sunday. Sunday?
Yeah.
Sunday.
Sure.
All right, sure. Oh, speaking of
Okay.
Sunday, yeah, I'll fix the schedule now, so we'll go 5 to 7 on Sunday, right?
On Sunday, I'm not sure. I'm not
You're not
sure when
sure
I'll get
yet.
back home. Could be 5 to 7 or 6 to 7.
All right, so we'll. Okay, so in that case, I'll just check then. Make sure you update me beforehand, so you
Yeah.
don't. So you know, if you're late, you don't get charged for it. Yeah.
Mm-hmm.
All right, so we'll end it here then. We'll see you on Sunday. Hopefully on Sunday. Bye bye, CJ.
Thank you. Bye.
Here's my window. Oh, here it is. Okay, so CJ's done. We're done with the class. For those who listen in, thank you again. Yeah, getting even I am getting more and more supporters, viewers at least. So okay, hopefully that was all okay for you. Any communication platform on the channel? Akira, that's a good question. Let me get to that now. I do. So I haven't done it much this week, but whenever we go to stream, I usually announce it here in either Instagram, Facebook, or TikTok. So these three would get announcements. So if you want to look forward to the stream, yeah, just follow us on either any one of these three. Okay. Now, whichever one, it's up to you, whichever you prefer. Now, where do I stream? I stream live on Facebook as well, of course, YouTube, and in Twitch. So the live streams are on Facebook, YouTube, and Twitch. But updates for when streams are gonna come up are usually on TikTok or Instagram, and also sometimes on Facebook. So there. So that's the main community. Those are the two communication channels. Okay. So I try to do it on YouTube as well, but it's not as easy to do it at once. I have to do it separately for YouTube. Sometimes I don't have time to do it. All right. Anyway, usually, I like I said, I haven't done it this week, but usually I post uh streams 30 minutes to an hour before the stream starts. So you should be notified well before the stream usually. All right. So okay, thanks. No problem, Akira. Just follow me on either one of those, any one of those. Okay. All right. Any other questions from anyone? If not, we have. That's basically it. All right. Let's just recap that quick. So again, energy production. There are many ways to think about it in terms of energy production. Types of energy, or sources of energy, or the actual modes of producing those energy or the electricity. Um, okay, so I think we'll end it here. So if you don't have any more questions, I'll wait another minute or so for questions. So let me rant for a minute. uh, oh, it's all. I didn't even realize the time. I knew it was an hour lesson, but somehow the time didn't register in my head. It's already dark outside. Very dark. We started the stream. There was still a bit of daylight. All right. Okay. Let me just go straight to the YouTube. No, not YouTube. Let's go to the chat features. Where is it? Okay. Let's get there. Hmm. Well, guys, I just want to say something totally unrelated to physics. I am in need. Well, not need. I want to have a new laptop. I want to have a new laptop for one reason. The laptop I have now still works, but it's starting to struggle with streaming. All right. Oh, it's not updating here. All right. So I think okay. Okay. So well, if you want to help me with that endeavor, a few likes and subscribes would help. It won't help financially, but it gives me the drive to continue doing this and gives you the drive to actually want to have a new laptop. Okay, so yeah, don't forget like, subscribe for YouTube. Don't forget to push that notification bell. Okay, so with that, I will greet you all a good day, good evening, good night, good morning, wherever you are in the world, and stay freaky, everyone. Bye bye now. Have a good day. Have a good one. Bye bye now.